Okay, back to our Ferris wheel problem. I just love this problem. It's a lot of fun and really instructive to see what happens as you go around on a Ferris wheel and compare with your experience. Hopefully you've been on something that goes around at a decent clip before, maybe not as fast as this one. So we're down at point A. You're imagining maybe you're the rider at point A, sitting on a scale. Your feet aren't touching the floor, so all of your weight or apparent weight, whatever force you're putting downward on something, is on the scale. And so what's our free body diagram look like? Well, here I'm imagining the rider here is 75 kilograms, as told at the top. The scale, of course, is pushing up on the person. I can feel, just like when I'm sitting in a chair here, I'm pushing down on the chair. I can feel the chair pushing back up on me. So that is the same thing, but the chair is the scale here, right? And of course, it doesn't matter how you're moving, the gravitational force from the Earth always pulls down on you with magnitude mg at the surface of the Earth. And you may, it's not clear that there's no friction force from the seat. We're hoping we're not sliding on the seat. But it may be that there's a static friction force from the seat. If you like, you can put in an unknown friction force, either to the left or to the right, and we can show later on that that unknown friction force is 0. Okay, at this point in the motion, so we're going around at constant speed, right? So at this point in the motion, your acceleration is toward the center of the circle. That's upward at point A. So I've drawn in the direction of the acceleration, even though technically that's not part of the free body diagram. Sometimes it's useful to just note it on there. And therefore, when I choose my axes, we could take plus x to the right, but the important thing is that one of my axes aligns with the known direction of the acceleration. So I'm going to take plus y to be along the direction of the known acceleration. Okay, and then we're going to do F net y, or sum of the force y components, equals may. And there are two forces with non-zero y components. F scale comes in with a plus sign in front of it, and the mg comes in with a minus sign in front of it. So we see those two there added together, sum of the force y components. And that's equal to the mass of the object in the free body diagram, 75 kilograms, times v squared over r, which is the magnitude of the acceleration, but the magnitude of the acceleration is the y component of the acceleration here, and the magnitude of the acceleration is v squared over r, 11 squared over 15. And therefore, I can calculate back out of this equation, the only unknown is F scale, and it's 1,340 newtons. Importantly, it's bigger than the rider's real weight, so that's the normal force that the scale would exert up on the rider. And here is the force that the scale is pushing upward on the rider at the bottom. That means the rider actually feels heavier. In every way, they feel like they weigh more. And you may have that experience as you round the bottom of something that's moving in a vertical circle, that you feel pulled down, you feel heavier, actually. Okay, in this case, if we assumed that there was a friction force, either going left or right, some sort of static friction force that the seat was exerting on you, we could do the sum of the force x components equals max. Ax would be 0 because I know it points vertical, and therefore this we could use this to show that the friction force actually had to be a 0 Newton force. So in this case, it's a combination of the gravity force and the scale force that cause the centripetal acceleration of the rider. It's a combination of the two. All right. What about at point C? That's at the top. I've circled it up here. Well, a lot of the stuff is the same, right? The scale, hopefully, is still pushing upward on you. Your weight hasn't changed just because you're still near the surface of the Earth, so it's still mg. And we could still take plus y to be up. It doesn't matter as long, we don't have to have it pointing exactly along the direction of the acceleration. It's just as good to have it pointed in the opposite direction of the acceleration. The important thing to realize is that the acceleration, as you're rounding the top, points downward towards the center of the circle. So that's really the only change from the previous case. So let's do F net y equals may. In this case, The left-hand side is exactly the same. For my chosen plus axis direction, F scale comes in plus, mg comes in minus. The only difference is now that when we set that equal to MAY, AY is actually negative, right? Going from tail to tip, we're going in the negative y direction. So AY is negative. We already calculated in the previous part that v squared over r was 8.07 in SI units. So this is 75 times minus 8.07. And when I add this part onto this other side, I have a positive thing plus a negative thing. So they actually cancel against each other, and we'll find that the scale force says that we feel lighter at the top. And you may have this experience from being at the top of a Ferris wheel as well. You sort of feel lighter, you feel your stomach go up a little bit. And again, same argument would show that the friction force is not necessary at the top. You don't need a friction force in order to keep you accelerating at that point in the motion. Finally, position B, again, in this case, the acceleration at position B is left towards the center of the circle, so I'm going to take plus x to be towards the center of the circle. The scale force still points up, the weight force still points down, but there also apparently has to be a static friction force because I know I'm accelerating to the left, and these two forces are not going to help with that fact. So there must be a static friction force pointing to the left. Let's figure out how big it is. Okay, first of all, if I sum forces along the y direction, still taking plus y to be up, some of the force y components would be equal to 0 because A is pointing in that direction. That means AY is 0, and that means F scale is equal to the weight, 735, just what we found at the very beginning. So your apparent weight is your normal weight here. Now the sum of the force x components equals MAX. In this case, the sum of the force x components would just be the static friction force. We'll just call it Fs, and that's equal to MA, and the mass of the object in the free body diagram is 75 kilograms, and the A we calculated in part C to begin with, and that was 8.07 in SI units. And if we multiply those together, the MA, we get 605 newtons. So static friction force has to pull on you quite a bit to keep you moving in a circle at constant speed. So in this case, we might be justified in saying the friction force is the cause of the centripetal acceleration. You know, most of the time people don't say things like that, but if you had to ask for a cause, the friction force, you know, these two forces clearly aren't helping at all to accelerate something to the left. Okay, let's now address a different question, which is, here's a video I found of someone on the web. Normally I would do this demonstration in front of you in class, and maybe I will on one of the days that we meet on campus. But here's a person with a bucket of water, and they're swinging the bucket in the circle. And the first question is, well, why doesn't, when the bucket rounds the top upside down, why doesn't the water fall out of the bucket? And the second thing you'll realize if you try to do this, that everything goes fine as long as you're spinning it sufficiently fast. But if you start to slow down too much, you'll start to get a little bit nervous. And if you swing it too slowly as it rounds the top, the string will become slack first of all, so the string won't stay taut anymore, and the water will in fact start pouring out of the bucket. So the question we want to answer is, what's the minimum speed at which we can spin this bucket of water on a string in a loop of radius r so the water stays in the cup when it's upside down? Feels like if you go too slowly that it's going to spill out, and that is indeed true. It's similar to this kind of problem. Maybe you played with Hot Wheels cars when you were a kid, and you have the loop in the track, right, where the car goes upside down and is completely upside down at position A. And the question is, well, why doesn't the car fall off the track when it's going around upside down like that? If you go fast enough, the car stays on the track all the way around. And analogous to that minimum speed question before, if the car doesn't go fast enough, it's going to fall off before it gets to the top. So what's the minimum speed the car can have so that it can make it all the way around the loop without leaving contact with the track? Someone actually did this in a real car a few years ago. I guess it had never been done before, but they built this track and someone drove a car in this huge loop. And it actually had to be fairly carefully done because human beings can only take so much of an acceleration in their body before you start to pass out. The blood gets pulled out of your head and you can actually lose consciousness. So this car had to go fast enough to make it all the way around the loop. You don't want to stall out at the top and fall off the track. That would be disastrous. So going fast is good, but if you go too fast, your acceleration would be really huge as you're going around in the circle, and you have a danger of actually passing out at a certain point in the circle. You don't want the driver to do that too, so they had a very narrow range of speeds that they had to approach with and round the loop with so that they didn't have problems doing this. In any case, we'll stick to the toy problem. All right, so since we're concerned with the top, that's when things seem most likely to fall out. If we imagine that we just really whip the car around, it's going around at a really fast clip, fast speed, well, it's on a circle of radius r. R isn't changing depending on the speed, but the v is, right? It's going around the loop, and its acceleration at the top is v squared over r. As v gets bigger, the acceleration gets bigger. So here I'm drawing an arrow that's fairly long, or at least I tried to make it look that way. That corresponds to a very fast speed. If v is big, v squared over r will be big. And that means the sum of the forces has to be big. And the sum of the forces acting on the car come from two sources. The car has mass, so it has its weight force that goes down. But there's also the force from the track that can push down. The track can't pull up on the car because there's no mechanism for the track to pull upward, but it can push downward on the car. And in order to result in this huge acceleration, the mg by itself isn't enough. We have to add on some additional f track going downward to get a sufficient net force going downward to result in that particular large acceleration, where v squared over r is pretty big. Now let's imagine what happens as we slow it down. As we go at a slower speed, we have a less long acceleration vector. That means the sum of the forces shouldn't be quite as big going down. Now the key observation is that the weight force can't change. The weight force is what it is, and it's not going to change depending on the speed. So the only thing that can change is the downward force from the track. So in going from a larger speed to a smaller speed, the acceleration goes down, and that means the track force has to go down. The track isn't pushing downward on the car as much. As we go still slower, the track pushes down less. And at some speed, the necessary net force that would cause the acceleration, which is given by v squared over r at that particular speed, would be exactly what is given by just mg with no force from the track at all. Okay? And if you went below that speed, if you were going to stay on the track would have to start pulling upward on the toy car. Now it has no mechanism to pull upward on the toy car. So if you go below that minimum speed at which the weight is just the right force to cause v squared over r in the circle for the speed we're concerned with, then that's going to be the critical speed. So the minimum speed that you can round the top with is when the free body diagram looks exactly like this. The track is just not pushing on the car at all as it rounds the top. Okay, now let's do F net equals ma. I'm going to take plus x to be down because that's toward the center of the circle. At the top, why not? And then we'll do sum of the force x components equals max. There's only one force x component, that's mg. And that's equal to the mass of the object in the free body diagram times the acceleration x component, which is that minimum speed squared over r, v squared over r. Cancel the m out and solve for v minimum. You get v minimum is equal to the square root of g times r. So if you're going slower than that as you approach the top, you're going to fall off before you hit the top. If you're swinging your bucket slower than that as it rounds the top, if it's moving at a slower speed than that relative to the center of the circle, the water's going to start falling out and the string or rope will go slack. before it reaches the top. So that's that critical minimum speed, which is kind of an interesting special case of this stuff. All right, there's a section in here that I at least want to mention that's called non-uniform circular motion that you read about in Giancoli, and it actually, non-uniform circular motion is exactly what it sounds like. You're going in a circle, but you may be changing your speed as you go around. Maybe you're speeding up as time goes on or slowing down as time goes on. And the upshot of it is, well, we can think of, if the object is here at the point shown, we can think of there being a radial direction axis and a direction of the axis tangent. We'll call that the t-axis, not time, but for tangent. And the analysis shows that the required radial acceleration is exactly what it is for uniform circular motion. So the radial component of the acceleration vector is v squared over r still, for whatever speed you're going at that instant. You know, your speed may be changing, but wherever you are at that instant, we use that speed, and there might be a bigger v by the time you get down there. But in addition to that, if you know the rate at which the tangential speed is changing, I guess I shouldn't call this the tangential velocity, but just the speed. The rate at which the speed is changing is called the tangential acceleration. And so if it's speeding up here, not only would I have a component of the acceleration in the radial direction, but if it's speeding up, I would also have a component in the direction along the direction of the velocity. So the velocity would be getting bigger. And so the real acceleration would have two components, a radial and tangential one. It would point not towards the center of the circle. The component towards the center of the circle would be the same, but it would also have a component going tangent to the circle. So it would point not towards the center of the circle. If it's speeding up, it points a little bit along the direction it's moving. If it's slowing down, it points opposite a little bit the direction of its moving. So that's what we use for non-uniform circular motion. The reason I threw it in here is because, you know, technically if this Hot Wheel is going around there, it's slowing down a little bit on the way up, right? And then it's speeding up on the way down. So this isn't technically uniform circular motion, even though the Ferris wheel problem, we could make the Ferris wheel go at a uniform speed. All right, let's take a break with that there.